Hello everyone, this is Jason. In previous chapters, we've learned the knowledge of ZW3D through Eksen. Now we will use a case to demonstrate the comprehensive application of 3X. The general workflow is same as 2X. Model preparation, add stock, tool creation. For the tool path creation in 3X, it includes roughing, rest roughing, semi-finishing, and finishing in general. Then the last step is verification. Now let's go to ZW3D and check. Firstly is the model orientation. We can do it in CAD environment. Add a stock and input the size you are going to use. Like this case, it's 150 by 110 and 42 mm. Then we can use move command. Select both stock and workpiece. Move to the origin. After that, we can erase the stock. Then the orientation is done. The second method, we can go to CAM environment, add a stock, the size is also 150 by 110 and 42 mm. Then we customize a frame. Create a datum first. Then select the datum. You can change other settings like name, clear Z, etc. This case, we use the default ones. Then we can generate tool paths based on the customized frame. In this case, we've put the model in the right position, so we'll just use the default coordinate system in the following operations. The next step, we need to analyze the workpiece, like the overall size, depth of the features, corner radius, especially the narrow areas. We can get the overall sizes in the steps when creating stock just now. We also can use the inquire commands, length, width, and depth. And the rough distance in some narrow areas. And also the radius. We will create tools based on this data. For the tool creation we've introduced in 2X tutorial, we are not going to repeat here. The tools we are going to use are listed here. Then we can start the toolpath creation. Firstly is the roughing operation. We use offset 2D. Just drag stock and part to the features. Select 10 mm bull nose and mule. For the parameter settings, let's say the material is steel. For tolerance and thick, 0.3 mm surface thick, 0.15 mm Z surface thick, 0.8 mm step down, and speed and feet are 5000 and 1500. For the above parameters, different companies may have different empirical values. Then calculate to get the roughing tool path. Through the workpiece analysis just now and observing the roughing tool path, we know roughly where the remaining material will be. Or we can use solid verify to check it. and save the rest material. Name it after first roughing. Now we can go ahead to generate the rest roughing toolpath. We've introduced 3 methods. In this case, we'll use ref operation. Just duplicate the rough offset 2D one. Use a smaller tool, 4mm flat end mill, and select the first operation as ref operation, and change the parameters accordingly, like speed and feet, 6,000 and 1,000. Because this is a demonstration case, in the following process, I will not set the speed and feet specially. You can set it according to the actual processing requirements. And set a smaller step down value, 0.6, and step over value, 35%. Then let's check the toolpath. Based on the analysis result after solid verifying the roughing toolpath, we know that the remaining material only located in these areas. So we will adjust the parameters to optimize the rest roughing toolpath. Try to change the Z surface thick to a bigger value, 0.2, and min rest height 0.6, and check the toolpath. It's much better now. The toolpath mainly falls in the areas where the remaining material is located. Then we can use solid verify to check again. For beginners, solid verify is an important command to check the status of the remaining material. This time we use the rest stock we saved before. We can see there's still some remaining material in the narrow areas, so we need to create one more rest roughing operation with a smaller tool. We save the rest stock again. To distinguish with the first one, we can name it after second roughing. Then we duplicate a rough offset 2D operation. This time, we will use another method to generate the rest roughing toolpath. Remove the ref operation. Select the tool 2mm ball end mill. Then add after second roughing stock to the feature, and also change some parameters like step down value 0.4, then calculate. Actually, we know the remaining material are located in these 2 areas, so we can make 2 contain profiles, this one and this one. Okay, then to optimize the lead-in toolpath, we can change the parameters here. Change the engage ramp height to 2 mm and angle to 8 degrees. Then the toolpath is much better. And we can solid verify to check. You can see the roughing is complete. Then save the stock. Name it after third roughing. Then next, we will create the semi-finishing operations to uniform the rest materials for the final finishing. The easiest way is to use angle limiting. Select the part as feature and use 10 mm bullnose end mill. For parameters, we specified at bottom point. Cut angle for lace pattern is 45 degrees and leave 0.1 mm for finishing. Then calculate. And for these narrow areas, we create another angle limiting operation. Same features, but use 2 mm ball end mill. Same surface thick, 0.1 mm, and cut angle 45 degrees. Then create a contain profile to limit the tool pass. Then calculate. We don't want the tool pass exceed the profile, so we can change the percentage offset to 0. Okay, then we have finished the semi-finished tool pass. Then we'll start the finishing operations. To ensure the surface quality, we need to process by regions. We will start from the middle section. For this vertical surface, it's better to use J level. And based on the previous analysis, the radius here is 3.5 mm. So we use a 6 mm ball end mill. Okay, then we select the outer profile and one of the inside circle as the feature. Remember, for all finishing operations, it's better to add part to the feature. Then check the tolerance and steps. The other parameters used the default ones. Calculate. We can see the tool pass cover the area we want to process, but for the slope area, tool pass is too sparse, and there are too many tool lifts. Then we can try to optimize it. First, let's change the step down value to absolute and 0.2 mm. Then angle range 10 to 90 degrees and short length limit 5. Let's check the effect. It's better now. Sometimes to get a better tool pass effect, you might need several parameter adjustments. Then are the internal recessed features. Because contours of the feature are circular, so we can use Offset 3D. Select these two circles as feature. Use 2 mm ball end mill. Then calculate. We can check the tool pass. And for the planar faces here, we will left them to the last operation. Then are the features on the right. Firstly, we will process the vertical surface. If you still remember, we've introduced the same in chapter Introduction of Finish Operation and Parameters. So here we can use Flow 3D. Select these two profiles as feature. Then use 2mm ball and mill and calculate. Then is the slope phase. We can select the whole profile as feature. And also use 2mm ball and mill, then calculate. You will see the toolpath will drop in the whole area, and there are several tool lifts. To optimize, we can create extra accessory surfaces. Then insert them to geometry. Then add them to feature. And set the cut angle to be 0 degree. Now the toolpath is much better. And for this flat surface, we will also leave it to the last operation. Then next will be the feature on the left. Firstly are the boundaries. The shapes are rounded, so we can use Offset 3D. We select these three profiles as feature. And use 2mm ball and mill, then calculate. For this part of toolpath, we can optimize it by adjusting the step over and the parameters of link and lead. Step over change to absolute 0.1 mm. Short link limit change to 1.5, and short link type used on surface. For the side features, because it's equidistant in 3D and has a slope in the y-x direction, so we can use Flow 3D. Select the two profiles. And use 2mm ball and mill. Then calculate with the default parameters, and this is the toolpath effect. And then will be the slope surfaces. We will process them one by one. First, we select this profile as feature. Then use 2mm ball and mill and calculate with the default parameters. You can see there are too many tool lifts and have some scaling toolpaths here. So we can adjust the cut angle 0 degree and short link type change to on surface. Then step over, we use absolute 0.2 mm, and the lead-in toolpath is too close to the vertical surface. We can change the engaged radius a little bit smaller. 2 mm is more safer. Then we can copy to reject. Then is the big slope surface. We can also use lace. Just select this profile as feature. Then use 2 mm ball and mill. Calculate. The toolpath seems good, but here also have some scaling toolpaths. We can use angle range to filter them out, like 0 to 10 degrees. Now the toolpath is better. And now let's show the previous toolpath, the level. You can see at the transition areas that were not covered fully by the toolpath. So we will consider to add toolpath here for a better surface quality. For these areas, we can use drive curve. Just select the outer profiles and limit the toolpath within the contained profile. Use 2 mm ball and mill, then calculate. The toolpath seems good, but we need the toolpath to offset several times, so we change the number of cuts to 6. And step over value, use absolute 0.2. This is the toolpath effect. And for this area, the lace toolpath cannot remove all the materials at this corner. We can use verify to check. So we need to use pencil cut to add toolpath here. Firstly, we can create a contain profile. Then use it and the part as feature. And use 2 mm ball and mill to calculate. As for the last remaining material, it depends on whether the need to use electroprocessing. Finally, we will process the planar faces. We can select the whole part to detect the planar faces, then remove those two have been processed. Then use 4 mm flat end mill to calculate. Since we finished all the operations, we can use Solid Verify to simulate the semi-finish and finishing process. Okay, that's all for the 3x cam case demonstration. Thank you.